Welcome to the last lecture of our post-mid syllabus. This is this lecture is on window sync filters. And if you remember from the previous lecture, we said that the moving average filter was a time domain filter, and this window sync filter is a frequency domain filter. The Even though we are calling it a frequency domain filter, know that there is still some effect of this filter in the time domain. But the reason we specifically call it frequency domain filter is because the frequency domain manipulation is more important here. The time domain manipulation is ignored. That means whatever it does to the time domain part of a signal is not necessary for us to know. And mainly the frequency domain parameters are what we tune in this kind of filter. Okay, so and the main use of this is in doing this work, that is separating one band of frequencies from another, such as low pass filter, high pass filter. All this can be implemented using some version of window sync. And of course, they have very good performance in the frequency domain, but this exceptional frequency domain characteristics are obtained at the expense of poor performance in the time domain. uh, and we have talked about this in one of our previous chapters, that any filter that performs well in the frequency domain will perform poorly in the time domain, and vice versa. The reverse is also true. So uh, by the fact that it performs poorly in the in the time domain means that it will have excessive ripple and overshoot in the step response. So the its frequency response, the window sync filter's frequency response will be very good, but its step response will have these characteristics: excessive ripple and overshoot, and both of them are bad characteristics to have in case of the time domain. Okay, and then before we start off with the window sync filter, we at first talk about what are the other basic filters that give rise to this window sync. So the first thing that we're going to talk about is the ideal low pass filter. So I think everyone already knows about this, the ideal low pass filter. We have seen the shape of it before already in some of our previous earlier chapters. That is, it will be something like this. Okay, so this is the ideal low pass, and this would be the ideal high pass. Okay, so ideal low pass, we can call the ideal high pass filter. And in figure A of 16.1a, we can see a figure of the ideal low pass filter. Let us just go here, and then we'll come back to the previous thing again. So this here is the okay, this this is the ideal low pass filter. Okay, and as you can see, it's ideal because first of all, it is a low pass filter. Why? Because it is allowing the low frequencies to pass from 0 to fc. These are the frequencies. Fc can be any arbitrary frequency, we don't know, but from 0 to this particular frequency, all the this frequency response is 1. Okay, so that means it is allowing these frequencies to pass. And then at fc, this is called the cutoff frequency. At fc, that is the frequency at which the cutoff frequency, that is the frequency at which it stops passing and starts uh, uh, starting the stop band. So here the stop band starts, and it starts instantaneously. If you just notice, right before fc it was allowing to pass, and right after fc it is stopping the passage. So when this happens instantaneously, this is called an ideal low pass filter. But in reality, this is not usually what is seen. That means this stoppage does not happen instantaneously. It happens somewhat like gradually, like this. So even though you were supposed to stop all the frequencies after fc, you do end up passing some of the later frequencies, okay, before you actually stop. So that is the characteristics of non-ideal low pass filters. But here what they are showing is the ideal low pass filter, that is this one, when it happens instantaneously. Okay, so if we think about the ideal low pass filter, in this is the frequency response of the ideal low pass filter. That means the instantaneous uh, transition band. There is no width of the transition band, it is instantaneous. So such a frequency domain, frequency response can be converted into the time domain by IDFT, and we will see something like this. So this is actually the filter kernel. That means the small h. That means the impulse response. So this is the small h, and this you can say the capital H. Okay. So this is the DFT version the capital H is the DFT version of the small h. So this is the small h. Actually, what we will convolute with in the time domain in order to perform filtering. So if we had to perform filtering, what we would do is we would just take an input and we would be performing convolution with this h, with this small h. And actually, its corresponding capital H shows us that this is actually a low pass filter, an ideal low pass filter. So remember that if this is the ideal low pass filter, its corresponding frequency to time domain would look something like this, and this function is a well-known function. This looks similar. I think probably you guys already heard of this before. So this function is called the sinc function. Okay, so this h corresponds to the sinc function. Okay, SINC sinc, and this is the next topic of our discussion here. This is actually the equation of h, small h, the sinc function. So this is the sinc function. Okay, and it's not necessary to exactly know the derivation of this, how it came like this. How we know that sine 2 pi fci by pi I is actually equal to this. Just know that this is what you are supposed to get. If you plot the values for different values of I, this is what you will get. The central value at 0, there will be the maximum amplitude, and this is like a sine function, but it will exponentially decrease in amplitude as you go to the right or left from 0. That means positive values and very negative values, both of them will give close to 0 value, but they will always oscillate around 0. See, it will never exactly become stable at 0. It will keep oscillating around 0. So one of the theoretical thing to notice here is that this is the sinc function is an infinite function. Okay, but we cannot store infinite functions, infinite signals in our system. So there will be a problem due to this. So this is the next problem that we'll be talking about. Okay, so this is the sinc function and this is infinite. That means I runs from negative infinity to positive infinity, and this never actually becomes stable at 0. So the problem is that the sinc function continues to both negative and positive infinity without ever dropping to 0 amplitude. This is what I just said. So, and because of this we cannot actually store it in our system, because our system, when we store it, we'll have to take a finite version of it, and that finite version will be an approximation of this, not the actual function. Okay, so to get around this problem, we will make two modifications to the sine function. So how do we actually work with the sinc function? So how do we work with the sinc function in case of a digital system that has a limited memory? So there are two things done in this case, but after doing them, what we get is the resulting waveform shown in C. Okay, so the resulting waveform shown in C, that means that this one, the truncated sinc filter kernel, this is obtained after doing these things. The first is it is truncated to m+1 points. Okay, so and m here is chosen, this m+1 points here, m is chosen symmetrical, the points are chosen symmetrically around the main lobe, where m is an even number. M is always an even number, so that there are symmetrically equal number of points to the left and right. Okay, so if m is any arbitrary value like maybe 7, then 7 plus not 7, it should be an even number, so 8 plus 1 9, then we will be getting 9 points. So here we can actually and these will be chosen symmetrically, not from the left, not starting from the left. It will be chosen starting from here, 0, the symmetry position. So from here, how can we choose 9 samples? We'll be choosing some samples from the 4 samples from the left, 4 samples from the right, and 1 sample from the middle. So that's how we get 9. Okay, so it will always be 1 sample from the middle, then some from the left, some from the right, and this how much will be determined by m. If that means there will be m by 2, m by 2, then plus 1. This 1 always comes from the central sample. Okay, so this is how we are going to choose m by 2 from left, m by 2 from right, and 1 from the middle. That is how we totally get m+1 points. This is how m+1 points are chosen. Okay, so all samples outside these m+1 points are set to 0 or simply ignored. Second, the entire sequence is shifted to the right so that it runs from 0 to m. So originally it was something like this. There were some values to the left which were having negative sample number. That means the indices were negative. But if you want to store them in an array, that array in any most of the arrays in most programming languages, you'll see that it either starts indexing from zero indexing or one indexing, such as in case of MATLAB it is one indexing, and you never get negative indices, right? So if we had to store them, we would be storing it from starting from zero. So that is why when you take m+1 points, you have to shift them in a way before, so that you can store them and reference them using an array or matrix or whatever. So for that you'll be shifting by how much? The amount is m by 2 actually. You'd have to m by 2 plus 1, or probably m by 2. Let me check. If I shifted m by 2 samples to the right, yeah, I'd be getting exactly all the samples will be to the right. That means I'll be getting all m+1 samples after 0. So from 0 I can start the counting. So here, as you can see, from 0 the counting can be started, and all the necessary samples that I took, the m+1 points, those will be all in the positive side, the positive region. Okay, up to m. So from 0 to m, I have total m+1 points. For that I had to shift by m by 2 right shifting. Okay, so that is what I'll have to do. So these are the two things that are done. The first thing is truncation, and then truncation of two m+1 points, and then second is shifting to the right by, actually the value is not given here, but it is actually m by 2 right shift. Okay, so this allows the filter kernel to be represented using only positive indexes. Okay, so now since the modified filter kernel is only an approximation, and note that this even after doing this, what the filter that we get is not the actual filter kernel. This is a approximation of the actual filter kernel. The ideal version would be infinite, but this is finite. So this is why it's an approximation, obviously, and it will not have an ideal frequency response. So this one had an ideal frequency response. That means an instantaneous shift. But this one, since this is not ideal, so its frequency response will also not be ideal. It will be gradual, and also there will be other problems like ripples, some passband ripples, and also stopband attenuation. That means it is not exactly becoming zero. It is oscillating and gradually becoming zero, but still oscillating. So that is the problem here. And to find the frequency response that is obtained, the Fourier transform can be taken on the signal in C. That means this approximation version, we can take the Fourier DFT on it, and then we'll get this. Okay, then after getting this, we'll see that this is completely different from the previous one. Lots of things have become bad here. So it is a mess. By mess, you know what it means. There we are getting excessive ripple in the passband and poor attenuation in the stopband. Okay. So in case of passband, we are getting one problem, that is the ripple. In case of stopband, it is not becoming zero directly, it is attenuating, and that means it is somewhat getting close to zero, but not actually becoming zero. So these these two problems will be seen after we do this approximation. So these problems result from the abrupt discontinuity at the ends of the truncated sinc function. So actually, these two new problems that happened, one is the ripple and the other is the stopband attenuation. This one happened mainly because even after taking this, we'll see that actually it was not supposed to end like this. Every age function, age signal, this age, after this point we have no other samples, so it's as if we have made all the samples zero, right? So all the samples after it we have made zero, and also before this sample we are considering that all the samples were zero. So the problem that happens is that suddenly this shift to zero, it happened abruptly, it did not happen gradually. Okay, like it was some negative value here, suddenly it became zero. Also it was some negative value here, suddenly it became zero, right at the next point. So that is what we are trying to avoid. It would have been better somehow if we could somehow make it so that it was not like negative to zero. If it was something like this, if its trend was gradually going to zero, here it was not going to zero. Okay, it was not actually going to zero. It's we forcefully made it zero. But this one, it seemed as if it was continuous. This is a continuous curve that was gradually going towards zero. So it would have been better if on both sides we could do something like this. Okay, so for that, what we usually do is Uh, okay. So for that, what we usually do is uh, there is a simple method to solve this problem. That is, we can in figure E, we'll see a smoothly tapered curve called the Blackman window. Multiplying the truncated sink by the Blackman window results in the windowed sink filter kernel shown in F. So this is the Blackman window shown in E, figure E. If we multiply, by multiply we mean point by point multiplication. If we directly point by point multiply the Blackman window or the Hamming window, we also talked about this before in one of our earlier chapters, probably in applications of DFT, in spectral analysis. We showed something like we were multiplying with the Hamming window. We did not say why. Also, we could alternately multiply with the Blackman window too, but we did not say why we were doing that. The reason is it will improve this scenario. This abrupt change to zero, it will make it gradual. Okay, so after we multiply, it will look something like this. Notice that it did not abruptly suddenly get close to zero. It was gradually becoming zero even before coming to this point. See, it was gradually becoming close to zero, and here as well. Before the n number of point ended, it was gradually becoming close to zero. So it remained continuous. Okay, so this is the thing that we usually do for this for getting this thing. Either multiply the Blackman window or Hamming window. Both of them look like a bell curve, but just one is like this and the one other one is probably like a bit sharper. So anyway, we can multiply with either of them and then we will get this thing. And this is actually the windowed sink filter kernel. Okay, the one that has a gradual tapering towards zero. This is not the windowed sink. This is the truncated sink filter kernel, and this is the actual windowed sink. The name of our chapter mainly depends on this one, and the windowed sink filter. The name of this chapter is mainly about this one. The result of the multiplication of Blackman or Hamming window with the truncated sink. Okay, so this is how we obtain the windowed sink filter kernel. So the windowed sink filter kernel actually is an ideal low pass filter. Uh, in the time domain, we'll get the sink obviously. In the frequency domain, we know what it looks like, but in the time domain, this is actually the sink. So after converting it to the time domain, uh, then truncating it. Okay, so we get the truncated sink filter, truncated trunk sink, and then we multiply with the Blackman or Hamming, Blackman window or Hamming window, either of them, and then we finally get this thing. Okay, the windowed sink. So this is how the windowed sink comes. Anyway, so the windowed sink is actually the product of this sequence of operations. So this is how we finally came to this. And remember in one of our earlier chapters, I told you guys that in chapter 16 you can find the equation of the Hamming window and Blackman window. Well, here they are. So the Hamming window and Blackman window, finally you can see the equations for them, why they are like this. So this is actually the equation of the Hamming window. This is a cost curve that gets subtracted from a constant value. Also, this is addition of two cost curves of different frequencies, 2 pi I, this is 4 pi I, and both of them, one is negative, other is positive, and the final thing is they are getting added with the 0.42 constant value. So both of them actually look like something like a bell curve, only the difference is that one is a sharper bell curve and the other is a like a slower kind of bell curve. Anyway, so that's all about Blackman and Hamming window. Okay, so as you can see, Hamming and Blackman. Hamming is this one, the upper one. This is actually the Hamming window, and this is the, and their corresponding frequency responses are like this. Uh, if you can see the differences between them, one has a faster roll off, that means a sharper, steeper roll off, and the other has a slightly less steeper roll off. But in this regard, it seems that Hamming window is better because its roll off is sharper. So it seems that Hamming window is better. But if you look at their stop band attenuation, then you'll see that window is actually better in this regard. So this is actually the stop band attenuation of Blackman, and this is of Hamming. So notice that it will take a long time to get close to zero, but this one is already getting closer to zero. So this one is better than this. Okay, so that is the topic of our next discussion. That is, there is a trade-off between the parameters. So you cannot directly say whether Hamming window is better or Blackman window. There is a trade-off between them, and this trade-off is actually the Hamming window has about 20% faster roll-off than Blackman. So in terms of roll-off, Hamming is better. But in figure C, that means in this figure, you'll see that C shows that the Blackman window has a better stop band attenuation. So this one has a better stop band attenuation. This one reaches zero faster than Hamming. So in general, the Blackman should be our first choice. A slow roll off is easier to handle than poor stop band attenuation. So most of the time, uh, most of the frequency domain applications, we prefer the Blackman window rather than Hamming window. That is because uh, what they are saying here is that low roll off, that means if you have a bad roll off, it is easier to handle. That means the effect will be less severe than a poor stop and attenuation. That means something that takes a long time to reach zero. That means actually it won't behave like a low pass filter, because the low pass filter is supposed to stop here, right, at FC, cutoff frequency. But even after the cutoff frequency, if it allows a lot of other frequencies, then that is a problem. Right. So that is the reason why Blackman window is mostly is better in this case. So there are other windows we might hear about, and they are like Blackman and Hamming, but they have a kind of less performing criteria than this. So those are not mostly used, but you can still know about them. One is called the Bartlett window, and it is actually a triangle filter. Triangle window. Okay, so that was a bell curve, Blackman and Hamming. This one is something like this. Okay, so this is Bartlett. So this bell curve was for Blackman and Hamming, and this would be a Bartlett window. And the Henning window, also called the raised cosine window, is given by this equation. Okay, so this is the equation for Henning window. This would obviously look something similar to Hamming window. Notice that there is a similarity in the equation, but obviously this would also be a bell curve. But the problem is that these two windows have about the same roll-off speed as the Hamming, but worse stop band attenuation. So both of them are actually bad because they have almost the same roll-off, but in terms of stop band attenuation, they're even worse than Hamming. So no point in talking about them further. Now, next we talk about how we design a window sync filter. To design a window sync, two parameters are selected: the cutoff frequency FC and the length of the filter M. So FC and M, these are the things that we can control about a window sync filter. And by controlling these, we can actually make the frequency response look differently. Okay, so if you change M, you can change the roll off. Okay, so M here is actually the kernel length. Okay, so M is the kernel length. So if you change the kernel length, that means if you take more number of points to represent the kernel, you can get a better roll off. So this is the roll off for this one. This one is the roll off for M equals 40. This one, this is slower, takes a long time to. Okay, so from 1 to 0, this one takes a longer time. So this is for M equals 20. So if you take less number of points, you can see that the roll off is slower. Here the roll off is faster, it is steeper for M equals 40. If you take M equals 200, it becomes even better, almost close to ideal low pass filter. See, it is almost vertical. This one, this is almost vertical. So this one happens when you take a huge number of points to represent the kernel. So this is the relationship between roll-off and kernel. Increasing kernel length will increase will make the roll-off faster. And this is in case of the cutoff frequency, the roll-off, the relationship between roll-off and cutoff frequency is that where the roll-off will happen. Okay, so the roll-off can start here if the cutoff frequency is 0.05. If the cutoff frequency is 0.25, then it will be shifted to the right. The roll-off parameter won't change. It won't become steeper or slower. It won't become faster or slower. This won't change. The only thing that will happen is that its position will be changed. Instead of happening here, it will happen here. Okay, here all of them were in the same position. in this location. Okay, but here their location is changing. If you set the FC as 0.05, it will happen here. If you set FC as 0.25, it will happen a bit to the right, and so on and so forth. The value for M sets the roll off according to this value. M equals 4 by BW, where BW is actually the width of the transition band, measured from where the curve just barely leaves 1 to where it almost reaches 0. So this is actually the relationship that you can use to find out how much time will be taken to reach from 1 to 0. Okay, so if I just erase all of these things, it will become clearer. Uh, okay, so this was the time. If M equals 20, then this is the time for this curve to reach from 1 to 0. Okay, so BW, the transition bandwidth, is actually this. This is actually the transition bandwidth. This is BW in that case. This link is BW. So if M equals 20, if you put 20 here, then 4 divided by BW is close to 20. So in other words, you can find BW by putting BW here. 4 divided by 20, that will be the actual bandwidth. Okay, so this is actually in that case 4 divided by 20. But if I now change M from 20 to 40, in that case what I am supposed to get is, okay, so if I use this one, it actually starts from here and ends here. So this is actually the bandwidth in that. This is the bandwidth. So the bandwidth of this will be not 44 by 20, this will be 4 by 40. The length of this is obviously smaller, so this one is 4 by 40. Okay, so this is how you would find the bandwidth using M, and these are not exactly equal, something close, as you can see. This is approximation set. Okay, so that is all about the bandwidth and the size of the kernel, the relationship between them. Now, and of course here bandwidth is actually expressed as a fraction of the sampling frequency and must be between 0 and 0.5. Notice that normally when we talk about bandwidth, we say that it is this many, in terms of bit per second, it is mbps or kbps or something like that. But if we talk about hertz in analog signal frequency, in that case bandwidth is actually in hertz, kilohertz or megahertz, something like that. But here the value that we will get, this will be from 0 to 0.5. If you multiply that value, that fraction, with the actual sampling rate, then you will get the actual hertz in hertz unit, the bandwidth in the hertz unit. Okay, now let us move on to, okay, in 16.3b, the cutoff frequency of the window sinc filter is measured at 1/2 the amplitude point. Okay, 16.3b. So this one here, FC is determined at 0.5 of the amplitude point. So this location is actually the cutoff frequency. So 0.05, obviously this is coming from, and where will we take the FC? The cutoff frequency is actually that region, that frequency at which we are considering that it is changing state from 1 to 0. But actually it started here and it is ending here. So which point am I actually going to take as FC? The starting point, the ending point, or the midpoint? Most in this scenario, we are always taking 1/2 of the amplitude point. Wherever it reached 1/2 of the amplitude point, that will be considered as the FC region. So this one here, it reached 1/2 of the amplitude point. Between this whole region, this is the point at which we were half of the amplitude. So this region will be taken as FC. So the actual thing that could have happened here, we could have taken this one as FC, this one as FC, but we are actually taking this one, the midpoint, as FC. This is what they're saying. And why we are using, now the reason why we are using half instead of the standard 0.707 that we use in analog electronics and other digital filters. So if you notice in the introduction to digital filter chapter, there I think I said something like this, that most of the time we use this in case of analog electronics and also in other digital filters. We use the 0.707 part of the amplitude as the FC. That means it would have been somewhere around here, 0.707. Okay, but in case of window sinc filter, we are using the halfway point. Why is that? Okay, So this is because the window sync filter's frequency response is symmetrical between the passband and the stopband. Okay, so if you look at the actual time domain character, what can I say, the plot, time domain plot of this filter, you'll see that it is symmetrical around sample 0, and at the even after truncating it, if you look at this truncated part, it is obviously symmetrical, not at 0 but at around some actual sample point. So that is the reason why uh, it is easier to work with a filter kernel whose frequency, the cutoff frequency, is taken at half of the amplitude. Okay, so as you can see an example that is given here. For instance, the Hamming window results in a passband ripple of 0.2% and an identical stopband attenuation of 0.2%. Other filters do not show this symmetry. So Hamming window, Blackman window, all of them, they show this kind of symmetry, and therefore uh, they do not. The other filters that do not have this kind of symmetry, they do not have the advantage of using half point as the cutoff frequency. And yeah, as shown in the later chapter, this symmetry will make the window sync filter ideal for spectral inversion. So if we consider the FC cutoff frequency to be at the halfway region, we will see that it will help a lot in case of spectral inversion. So we can get other versions of this, such as from LPAF low pass filter, we can get high pass filter using spectral inversion, and it becomes more accurate if we use the cutoff frequency as the halfway of the actual amplitude. Okay, so now FC and M. So FC is the cutoff frequency and M is the filter length. So after selecting them, the actual filter kernel can be calculated using this relation. So previously we have set the filter kernel to be something like, if you remember, hi was something like 2 pi fci sine 2 pi fci divided by pi I. So this was actually the simplistic version of the ideal sinc function. So this would have been the ideal sinc function, this function. Okay, so but now what we are doing is we are not taking this one. It should be noted that this equation here was the equation for the ideal window sync function. Okay, so but we are not using this actual ideal version. We are truncating it and then multiplying with the Blackman window and then picking a particular cutoff frequency, taking a particular uh, filter length M. So after doing all of that, we can actually get the compressed version, a single equation that will represent all of these things that we just did. That means all these steps that we just did, truncating, then multiplying with the Blackman window, and then picking a particular filter length, and all of this can be summarized into this one equation. So this one equation actually summarizes all of these things, all of these steps that we just did. So even though it looks a lot of largely complicated, but it is actually not. So just seeing this equation, you can get a lot of things from here. Based on the previous discussion, all the things that we just discussed, you should be able to identify three components from this: the sinc function, the m/2 shift, and the Blackman window. So if you look closely, you'll see that this is actually the sinc function. This equation is actually the sinc function, sine 2 pi fci by pi I. But one thing you will notice is that the m/2 shift actually comes here. The m/2 shift actually comes here in this format, I minus m/2, I minus m/2. So here comes the m/2 shift, and the Blackman window that we are multiplying, it is actually here. It is the product of this function with the equation of the Blackman window. Also, this can be replaced by another equation if you use any other window, maybe Hamming window, Bartlett window, Henning window. If you use any of them, you will just replace this part with their corresponding equation. So those are all of the things that have occurred here within this one equation. Okay, and also notice that there is a k here. K is actually chosen as such that the sum of all samples is equal to 1. That means this is just a normalization factor. Okay, so that was all about how we actually design the filter. So this is the actual designing of the filter. If you since we do not use the original window sync function, this is the modified sync function, where we incorporate all of those things, multiplying with Blackman window, taking a particular truncated version of it, all of these things. So that is done. Now, if you look at some different filter kernels and their corresponding step responses, you'll see the different kinds of shapes they may take and for different kinds of values. For example, FC, if the cutoff frequency is 0.015 and M is 500, then the filter kernel would look something like this and the step response would look something like this. Notice that if you change FC, that means the cutoff frequency, while keeping M constant, that means 500, M is still 500, but FC changed from 0.15 to 0.04. So it increased a bit. So if it increases, notice what happens in the corresponding step response. The ripples increase. So here the ripples were a bit wider. Here the ripples are of higher frequency and narrower and present in more compactly. And here you'll see that the peak increases. Okay, the middle peak amplitude increases when you increase the cutoff frequency. And if you keep the cutoff frequency same, okay, 0.04, here also 0.04, if you keep the cutoff frequency same but change the size of the filter and from 500 to 150, notice what happens. You just get rid of a lot of this. So you have a smaller window obviously in the kernel, and in case of the step response, what you have is you truncate the later part of the ripples. The later higher the ripples that you will get in the higher sample numbers and also in the lower sample numbers won't be there. They will be taken as zero. So these are some of the things that will happen if you change the cutoff frequency and the filter size. Okay, now we come to the final topic. That is, here we will see some examples of window sync filters in some what kind of scenarios we may be using window sync filters. Also notice that there will be another section after this, but that is not left for our discussion. We won't be discussing this, pushing it to the limit. This mainly discusses about the performance of window sync filter, how we can improve the performance, and lots of things here are actually highly related to triple A concepts and not exactly related to our field. So we'll be skipping this region, this entire section. So our final topic for this chapter will be the examples of window sync filters. So the first example that they're talking about here is the EEG, the electroencephalogram, which is a way to measure the electrical activity of the brain. So here there are, so this is just a knowledge-based thing that in most human beings, it is seen that about 7 to 8, 12 hertz, about in this range, the waveform is called the alpha rhythm, and this happens when we are in relax mode. So when someone is in relax mode, we close our eyes and relax. We are not focusing on anything. In that case, our EEG pattern will be showing a frequency of between 7 to 12 hertz, and this is known as the alpha rhythm. Okay, and then if we open our eyes and start looking around, focusing on different things, in that case, our brain signal changes to the beta rhythm, and this one is in this range, 17 to 20 hertz. Okay, so this happens when we do some activity, not any intensive activity, just looking around. So this is the beta rhythm. So in such cases, we might need a filter that would work in the frequency domain. Why? Because as you can see, we might want to separate out different frequencies. So it's different bands of frequencies. So band pass filter might be used here. So here they're showing an example of how something like this may be implemented. So the EEG signal, in this case, what would happen is the EEG signal would be amplified by analog electronics. And the reason for amplification is that sometimes some of the small things may not be visible if you do not amplify, or even the important data may not be visible if it is not amplified. So for that reason, it is amplified to a particular scale, and then it is sampled at any arbitrary rate. In this case, for simplicity, for this example, they are sampling it at a rate of 100 samples per second. Okay, and our goal is to separate the alpha from the beta rhythms. So from this region to this region, we want to get two separate signal components. And to do this, we will design a digital low pass filter with a cutoff frequency of 14 hertz or 0.14 of the sampling rate. Why 0.14? Because remember the sampling rate was 100 samples per second. So 14 is actually 0.14. So in this, since we are actually representing the frequency domain from 0 to 0.5, so 0.14 of the sampling rate would be somewhere around 0.14 would be somewhere around here. Okay, so and in this case, in the low pass filter case, it would be somewhere around here. Okay, so what we need is we want the low pass filter to separate out the alpha wave, and also the high pass filter would separate out the beta wave. So this is how we can get two different filters to give us two different waves, because we know that the alpha wave will be somewhere around here, the beta wave will be somewhere around here in our frequency domain plot. So if you want to separate them out, we'll need two different filters for getting these two different waves. And the low pass filter should be tuned so that the cutoff frequency is around here. If the cutoff frequency was here, then it would not be able to distinguish them. It will be thinking alpha wave and beta wave to be within the whole low pass region, so it won't be able to distinguish them. So this is the reason why we are selecting the cutoff frequency to be exactly at this hertz, because we see that this one allows us to easily distinguish between the two bands. Okay, so this is one scenario where we might be using a window sync filter. And just as we have said, window sync filters can be used for low pass, high pass, all kinds of scenarios. The discussion that we have done before, where we were deriving a window sync filter from an ideal low pass filter, that will give rise to this non-ideal low pass filter, such a window sync filter. If we started from an ideal high pass filter, IHF, IHPF, you can say the ideal high pass filter, if we started from that and did all those things like truncation, multiplying with the Blackman window and all those things, then we would have gotten this the window sync filter that would act as the non-ideal high pass filter. Okay, so this is how we could have used window sync filters for separating out the alpha wave and beta wave. There is a second example shown here where we are designing a band pass filter to isolate a signaling tone in an audio signal, such as when a button is pressed on a telephone. So you'll remember that when you press a button on a telephone, or maybe on your smartphone as well, when you press a button, suppose you are dialing a number, when you press a number, you hear a tone, and for different numbers the tone is different. You can actually test it out right now. 0 will produce one kind of tone, 1 will produce a different kind of tone. So you can type in different numbers, every time you'll hear different kinds of sounds. Now the thing is, why do we hear, how are we hearing different kinds of sound? So each of these sounds are produced by making a constant sound pass through a bandpass filter. So the thing is that suppose the actual sound is something like this, and every time for different kinds of buttons, different kinds of bandpass filters are used that will allow only a particular band of frequency to pass. 0 has a particular band of frequency, 1 has a different band of frequency, suppose something like this, 2 has a different band of frequency, something like this. So that is how we are, after passing some specific bands of frequencies, we are getting some specific sounds by pressing each of the different buttons. So in this case as well, we are assuming that the signal has been digitized as at 10 kilohertz, and the goal is to isolate 80 hertz band of frequencies centered on 2 kilohertz. So 80 hertz band centered on 2 kilohertz, it should be something like so if 2 kilohertz, if along the frequency domain 2 kilohertz is somewhere around here, okay, so 10 kilohertz, 0.5 of the sampling rate, 10 kilohertz would be 0.5. If we take 0.5 to be here, 0.5 of the sampling rate would be equivalent to 5 kilohertz. Okay, so that means the end point is equivalent to 5 kilohertz. Then 2 kilohertz would be somewhere near to the mid region, right? Not here. It would be somewhere near the midpoint. Okay, a bit here. So around 2 kilohertz, we want to take an 80 hertz worth of band. So this is 80 hertz. So this is the band of frequency that we want to isolate. So that means we would have to create a bandpass filter whose cutoff frequency, whose frequency would, the low pass filter would be starting at somewhere around 1.8, 1.2, not 1.2 exactly, it is actually 1960 and 2040. That means 40 from the left and 40 from the right. Total of the total will be an 80 hertz worth of band. Okay, so the actual values are actually given here, 1960 and 2040. So 2 kilohertz means this is centered at 2000 hertz. So 40 from the left and 40 from the right. This will be 1960 and this will be 2040. And this is actually equivalent to 2K, 2000. So in order to create such a bandpass filter, we would have the design would involve several steps. The first is we would need two low pass filters, one with a cutoff frequency at 0.196, the other with a cutoff frequency at 0.204. And next, the two filter kernels are added, resulting in a band reject filter. Okay, so if you add two filters, what we are supposed to get is if you refer to the previous chapter, you'll see that we will get, also another thing, we are not supposed to add two low pass filters in order to get band reject. In order to get band reject, we'll have to add a low pass with a high pass, right? Okay, so this was a low pass, this is a high pass, so we'll have to add them in order to get band reject. If you remember from the previous chapter, convolution of low pass and high pass produces band pass, and addition of low pass and high pass produces band reject. So for that to happen, we'll be creating at first two low pass filters, then one of them needs to be a high pass, so we'll be inverting this one. The second filter will be spectrally inverted, making it a high pass filter. So that high pass filter's cutoff frequency will be at 0.204. Then we'll be adding these two filter kernels, and as we have just said, addition of low pass and high pass will produce a band reject filter. But what do we need? We need a band pass, right? Something that will pass this band, these band of frequencies. So we have to just perform a spectral inversion to make it a desired bandpass filter. So this is the sequence of steps we would need to finally get a bandpass filter which will pass from 1960 to 2040. A total of 80 hertz will be passed. So this is how you are supposed to get it. So this is all about Windows Sync filters and some examples of how Windows Sync filters may be used in practical scenarios. The rest of the topics here are mainly about performance of Windows Sync filters and how changing one of the things may change other things. And these are mostly algorithms and triple E stuff. So we won't be focusing on this. And here the chapter ends. So that is all for our discussion. Thank you, everyone.